Welcome, and as we start week 9, it is a good time to look back at what we had done. So, we started with very simple oscillations of a single object, then we analyzed oscillations of coupled objects, many beads for example coupled together, and we were interested in the coupled mode of oscillation. In other words, what is the pattern of oscillation of all the particles together. And then we went beyond it, brought all the particles close together to form a continuum, and it gave us the wave equation. And from the wave equation we looked at transverse oscillations described by wave equation. We also looked at the longitudinal waves, which were also described by the wave equation. Prominent example of longitudinal waves are the sound waves. So, we derived a formula for speed of sound. We also looked at how the formula would change if we were describing sound propagating in a solid, and also what happens when waves in general and in particular sound moves from one media to another media. Now, what we will try to do is to address a reverse problem. For instance, we had done this very simple problem where we added two say sine waves with slightly different frequencies. So, let us say that this has a frequency nu 1 and this has a frequency nu 2, and the difference between them is really small. Nu 2 minus nu 1 you can assume is really small. Think of it as some delta nu. This, when we add them together, gave us something like a pattern of beats. Now, the question is, if I were given, let us say, this object, the combined waveform, can I get these individual components? So, that is what we are going to do today, and this kind of analysis requires this tool which is called Fourier series. I would say that some function is periodic if, let us say, f of x is equal to f of x plus alpha. Very simple examples of periodic functions are of course sin x, cos x. For example, I can construct a periodic function that looks like this. This is also a periodic function. Again, the question is the same. Now, can I analyze and find out what components of sines and cosines have gone into making this periodic function? The central idea here is that if I have any periodic function f of x, it can be represented in what is called the basis of sines and cosine functions. So, I can write it as where n can be a extremely large number. In principle, it can even go off to infinity. So, you will notice that the right hand side, which is this summation, represents a summation over large number of smoothly varying functions. So, which means that we require the left hand side, which is the f of x, also be a smoothly varying well behaved function. We can still have discontinuities which are finite in nature. For instance, if I had a function of this type. So, let us say that at x equal to x 0, I have this finite discontinuity in the function f of x. This itself is not a problem, can be taken care of by this Fourier series. Let me write the Fourier series in a compact notation. F of x is a 0 by 2 plus I have an infinite summation n going from 0 to infinity. So, I have written down the expression or the Fourier series in a compact notation involving the summation notation. So, the unknowns are actually the a n's and b n's. So, those are the quantities which we need to determine if we have to make use of this Fourier series. So, in general, if your function f of x is sufficiently smooth in the sense that it has only finite number of finite discontinuities, in all such cases the summation in the right hand side is known to converge. So, I am going to state this without actually showing you the proof. It is written in such a way that we can identify the discrete frequencies involved in making of this function f of x. So, this is another representation of the Fourier series, and it does not take much effort to figure out that C n square is equal to a n square plus b n square, and also that tan of theta n is equal to b n by a n. And another possible representation of the Fourier series is in terms of e power I n x. So, I have three different ways of representing the Fourier series. Depending on the problem at hand, sometimes one of these is more easier to handle than the other. In either case, whichever one that you choose to work with, you cannot escape from determining the unknowns. So, let us first determine a 0, and to do that all I need to do is simply integrate the function over the range of periodicity. So, here I will assume that my function f of x has periodicity 2 pi, cos n x and the sin n x integral both will be 0, because for example, sin 2 n pi for any value of integer is 0 as well. So, this integral is 0. So, clearly the cos n x integrated over 2 pi is 0. So, that would go away for all values of n, and you can do the same exercise for sin n x. So, integrate sin n x between 0 and 2 pi for any integer value n, that would also be 0. So, I am going to have the following result. So, now I have determined the value of a 0 in terms of the function f of x. To make this result a little more instructive, it is more convenient to divide it by 2 here and divide it by 2 here. And you will notice that the first term, which is a 0 by 2, is very different from all other terms in the series. All other terms involve some cos or sine function, oscillatory functions, whereas this one is really a constant. So, this is often called the DC level, or it is a constant that tells you where you are, and these oscillatory functions oscillate about this. The left hand side here is simply the average of the function f of x. Now, let us find out the other two unknowns, which is a n's and b n's. So, what I have done is to simply multiply by cos m x throughout the equation and integrate over 0 to 2 pi. So, a 0 by 2 can be taken outside, which is this term can be taken outside the integral, and integral of 0 to 2 pi cos m x dx will give you 0. This is something that we just saw, hence this term will go to 0. N and m are integers, we should keep that in mind. So, let us see what happens if n is equal to m. So, in that case this whole function would simply become cos square n x dx evaluated between 0 and 2 pi, and this integral is very easy to do. So, we are left with only pi as the answer. So, let me write the answer here. So, the answer is pi if m is equal to n. So, if m is not equal to n, you can use the cos a into cos b formula. So, the result will be in terms of cos a plus b and cos a minus b. So, this integral when m and n are not equal Now, you can integrate this function very easily, it is simply a cos function. So, the result will be a sine function. This entire function irrespective of the value of n and m until they are integers is going to give you 0 if n is not equal to m. So, this will be 0, this will also be 0. So, now I can again write the result of this integral as being equal to 0 if m is not equal to n. And similarly, I urge you to work out what happens if you integrate between 0 to 2 pi the sin n x sin m x integral, and this is equal to pi as well if m is equal to n, and it is also equal to 0 if m is not equal to n. Let us say cos n x sin m x integrated over dx between 0 and 2 pi. So, in such a case, irrespective of what m and n are until they are integers, the result is always 0. The integral here, for example, will survive only if m and n are equal, and this one is a combination of sine and cos integral, will not survive for any value of n and m, any integer values of m and n. So, this will always be equal to 0, whereas this one will survive if m is equal to n, in which case we will have, I need to do a very similar exercise to find out bn's. So, all I need to do is to go back to this the first relation that we wrote down for Fourier series, multiply throughout by sin m x and integrate over 0 to 2 pi. I have collected all the relations here. So, with this, in terms of integral over f of x, we will know all the coefficients, which are a m's, b m's and a 0. So, as I said, a 0 or a 0 by 2 gives you the average of the function, and these other coefficients tells you which frequencies are involved in the construction of the given function. Just to give you a pictorial example, for instance, I have this function here which I just plotted out, and you can see from the looks of the function clearly, if I take this to be the origin, this point here, if that is the origin, then clearly the function is oscillating about x equal to about y equal to 0. So, which means that the average of the function is 0, and the oscillatory components, if it is a pure sine curve, our analysis will tell us that only one term of this b m's would survive and everything else will be 0, and none of the cosine integral will survive. So, all the a m's will be 0 for all values of m, and b m, all of them will be 0 except 1, and a 0 is equal to 0. So, it is a simple exercise, it is very intuitive, you can try and do it. In other words, to do it more formally, you should assume that your f of x is sin x. The result of this would be that all a m's will be 0 for all values of m, b 1 will be 1, but all other values of b m other than 1 will be equal to 0, and a 0 of course will be equal to 0 as well. So, a 0 is related to the level, the average of the function, and just by looking at it you can very easily say that the average of the function is 0. What we know is that if I have a function f of x, a periodic function f of x, I can write it in the following manner. To understand what is happening, let us take a simple example. This function would be called an even function, because under the transformation that x goes to minus x, f of x is equal to f of minus x. So, you put x equal to minus x, the function does not change, and in fact you can even plot the function. So, it would look like this. So, it is a quadratic function in x. So, on the left hand side of the equation that I have written down, I will have x square, and this will be half of f of x is of course x square plus f of minus x for this choice x square will be x square itself, and again half f of x is x square minus f of minus x is x square. So, clearly the second term will go to 0 and the first term gives you x square itself, which is identity. The point that I am trying to make is that you can write any function f of x in the form that I have written down here. So, there is one part, the first part which would be which would survive if it is an even function, and then there is a second part which would survive if it is an odd function. So, this is f of x equal to x cube. This is an odd function. Under the transformation that x goes to minus x, f of minus x will go to minus f of x. The x square function is symmetric about this line, which is x equal to 0 line, whereas this one is sort of anti-symmetric. The sine functions are odd functions. Sin x is an odd function about x equal to 0, and similarly cos function cos x is an even function. The cos x function has expansion in terms of x square, x power 4, x power 6 and so on, whereas sine function has expansion in terms of x, x cube, x power 5 and so on. This general result for f of x that I have written down, it says that any function can be written as an even function plus an odd function, and clearly our Fourier series is in that form. So, if my f of x is an even function, then the only contributions would come from the cosine basis, which means that all the AMs would be non-zero and all the BMs would be 0. So, this is the gist of what we just learnt about the symmetries of the function. So, if your f of x, the periodic function, is a even function, then all the contributions will come only from the even part of the expansion, which is the cosine part. Hence, all the AMs will be non-zero and all the BMs will be 0. So, if you know that your function originally is a even function, you do not even have to calculate the values of BM. And similarly, if you know that your function is an odd function, then all the AMs are 0 for all values of m, and you need to only calculate the values of BM alone. But in general, if your f of x does not have any particular symmetry, of course, there would be contributions from both. With all this understanding, now let us do one non-trivial problem. So, the problem is, I have this periodic function which I have drawn for you here. Analytically, it is described as follows. Clearly, the function is periodic, as you can see. So, the basic periodicity, for instance, you can take it either from 0 to 2 pi or from minus pi to plus pi. So, one thing you will notice is that the function oscillates about y equal to 0, which means that the average level of the function is 0. So, without doing any calculation, I can say that the DC level or the steady state level is 0. So, A0 you should get as 0. That is one thing. Just look at the part of the figure between minus pi to plus pi. So, you will see that it is an odd function. We just now a while back argued that if we have an odd function and if we are going to do Fourier analysis of an odd function, the only surviving terms will be BMs, B for all values of m, and all the AMs will be 0. In other words, the cosine series should all be 0. It is only the sine series that will survive. So, let us first calculate A0. the standard formula which we just derived is already given here. And now if I do it between 0 and 2 pi, one complete period, I need to split the integral into two parts, because my function is defined differently between 0 and pi and differently between pi and 2 pi. Okay, you can see that here. So, I can rewrite this as 1 by 2 pi integral 0 to pi f of x dx plus pi to 2 pi f of x dx. So, this is something we expected based on just looking at the function. Now, let us calculate the AMs for values of m other than 0. So, to find AM, again we do the same technique of splitting the integral between 0 and pi. It is easy to do this integral. Both the integrals will give you a sine function, and the sine function is 0 at every limit of this integral, at 0, at pi and at 2 pi. So, the answer is going to be h by pi multiplied to 0. So, the answer is 0. So, the result is that AM is all equal to 0 for any value of any integer value of m. This is something that we guessed based on the fact that this function is a odd function. Now, finally, let us calculate BMs. So, let me quickly do the calculations. So, 1 by pi, and integrating these functions are simple because both are cost functions. So, let us quickly do that. So, that is going to be h by pi. So, I am going to get minus cos mx by m between 0 to pi minus cos mx over m between pi and 2 pi. If you put in the limits, this is going to give me, so this tells us that Bm is equal to 0 for even values of m. Bm will be equal to 4h by m pi for odd values of m. So, this was the Fourier series expansion that we initially wrote down, and now we know that A0 is 0. So, this term will not exist, and we also know that all ANs are 0, this term also will not exist, and from what we just did, we also know that BMs survive only if m is a odd integer. So, the first surviving term will be n equal to 1. So, that will be sin n is 1. So, it is sin x. Next term will be sin 2x, but we have said that even n's the value of Bm is 0. So, that term will not exist. So, the next surviving term will be sin 3x, and of course, there will be a divided by 3 here because of this n, plus sin 5x divided by 5 and so on. So, this series that we have obtained represents this function that we have drawn here. So, you can see what we have achieved. So, we have this function which has finite discontinuities at several places, at pi, at 0 and so on, and now all that is represented in terms of an infinite series in terms of sine function. So, that is what you get when you Fourier analyze any periodic function.